Okay, so now we're going to go into talking about the R and S notation that we use for chiral centers. Generally, we can assign chiral centers. Remember that when you have a chiral molecule and a chiral center, these always come in pairs. And so they can be assigned a configuration of what we call R or S to their stereocenter. And these are just based on a set of rules and their orientation. Generally, what this refers to is the direction of rotation that these molecules exist in, where R is to the right. You can think of it, but really it means clockwise. You'll see an example of this in a second when we're assigning. And S is to the left or counterclockwise. So any chiral center, any molecule with a chiral center can also have that center assigned as an R or an S center. And to do this, there's a set of rules. The first thing you want to do is prioritize the groups around the center by their atomic number generally, where higher atomic numbers are at the first point of difference, give a higher priority. So this example here is pretty straightforward. You can see we're looking at a fluorine, a bromine, a chlorine, and a hydrogen. And again, we're going by their atomic number. Okay, that's the bigger atomic number, the more priority they get. So if you were to look at a periodic table, bromine has the biggest, highest atomic number, so it gets priority 1. Chlorine then is second, fluorine third, and hydrogen, of course, is the smallest of the atoms, and so it will get the lowest priority 4. You're then going to point the group with the lowest priority, that's priority number 4, kind of into the page. So we're rotating that hydrogen. Again, we'll look at them here. We're rotating it so that the hydrogen is pointing away from us into the page. And you generate kind of this like half Newman projection. So we're not looking via a bond, a carbon-carbon bond, but we still are generating a projection in which you're only looking at the front 3 bonds with the hydrogen bond going in the back. Now, once you do this, you're going to examine the direction of rotation from 1 to 3. So remember where you numbered things. In this case, our bromine is here. Remember that was given 1, chlorine was given 2, and fluorine was given 3. And so if we were to draw an arrow connecting these, it would look like this. Here, 1, 2, 3, our arrow would look like this if we connected it. Now, once you have drawn that arrow connecting 1, 2, and 3, you can decide if it is an R or an S configuration. Remember, R is clockwise and S is counterclockwise. So molecule A has a R configuration and molecule B has an S configuration. So these are enantiomers, they're chiral, and you'll always see that the mirror image of an enantiomer will be the opposite configuration. So if one is R, the other is always S. So let's go more into these rules of prioritization, how you assign things, because it can get a little bit tricky sometimes. Generally, as I said, you always want to use the higher atomic number. That takes precedence over the lower. So like in our example, bromine would have priority number 1, chlorine 2, fluorine 3, and hydrogen 4. What about if you have chains? So when two atoms are directly attached to a chirality center and they are the same, you're then going to compare the atoms attached to them on the basis of their atomic number. So we're still using atomic number. And the precedence is just determined at the first point of difference. So wherever they first become different, that is where you will then decide. So here, this carbon is attached to a chlorine, a hydrogen, and then it has these carbon chains. So if we were to look first, this is carbon, carbon, hydrogen, or chlorine. We know that chlorine is still going to get number 1, and hydrogen is still going to get number 4, but this is a carbon and this is a carbon, so how do we assign these? Well, this carbon here is attached to 2 hydrogens and another carbon. And this carbon is attached to 2 hydrogens and another carbon. So there's no point of difference yet. So we're going to move on to the next point along the chain. This carbon here and this carbon here. This carbon is attached to a carbon and 2 hydrogens. This carbon is attached to a carbon and 2 hydrogens. So again, no point of difference. So let's move one more time down the chain. This carbon is attached to 3 hydrogens. This carbon is attached to 1 carbon and 2 hydrogens. So you can see that hydrogen has a lower atomic number, and this has an attachment with at least 1 carbon, and carbon has a higher atomic number. So at the first point of difference, you're going to use the atomic number of the atoms attached. So this one has a carbon, this just has hydrogens. So this would get precedence, it will get position 2, and this gets 3. As I just did, make sure that you always work outward from the point of attachment and compare all atoms attached to a particular atom before proceeding further down the chain. So when you look at this one, here's our chiral center, and we want to decide priority here. Remember that there is a hydrogen, it's hiding. When you look at this at first, you might say, oh, well, there's a chlorine here, so this is probably going to get the highest priority because I can see there's a chlorine and chlorine has a higher atomic number. But you always want to work outward slowly. So here, attached to this carbon, there is a carbon and a carbon and a carbon. So that doesn't help us. But what are those carbons attached to? Well, this top carbon here is attached to 3 hydrogens. It is a CH3 group. This carbon is attached to 2 hydrogens and another carbon here. This carbon is attached to a carbon and another carbon, and it has a hydrogen on it. So this group in the bottom actually gets higher priority because if we want to look at the chains again, we have 3 hydrogens versus 1 carbon and 2 hydrogens versus 2 carbons and 1 hydrogen. So this gets priority. Even though there is a chlorine here, it's further down the chain, and because we're always going to work outward slowly at each point, comparing them before proceeding, that means that this gets highest priority, followed by this chain, and then this chain, and of course, last would be our hydrogen. And again, when working outward from the point of attachment, always evaluate substituent atoms one by one and never as a group. So do it as I was saying, where you're going to be thinking of at each point what is attached to, and not as what is it attached to further down the line, what is its group attached to. So here, again, we have this chiral center attached to a carbon, and a carbon. So in this case, this carbon here is attached, as before, to 3 hydrogens. This carbon here is attached to a carbon, a carbon, a carbon. So it has 3 carbons on it. Now this carbon, if you want to look closely at it, it has a hydrogen, but it also has a chlorine directly attached to it. So it would be hydrogen, hydrogen, chlorine. In this case, remember, we're always comparing by the atomic number. This carbon does have higher precedence because when directly comparing their attachments, this carbon is attached to a chlorine compared to hydrogens or carbons. So in this case, in our direct comparison, we would say that this group gets highest priority, followed by this group, and then this group. Now, if you have an atom that is multiply bonded to another atom, it is considered to be replicated as a substituent on that atom when you're counting its attachments. So here, again, we have our chiral center. This carbon at the top is attached to 3 hydrogens. This carbon has an attachment to another carbon up here and 2 hydrogens down below. This carbon has a double bond. And in this case, it also has a hydrogen here. So we would count this carbon as having a hydrogen and being connected doubly to a carbon. So it gets carbon, carbon, hydrogen. So when comparing these, you will see that the double bonds, when directly comparing this single bond to a double bond, the double bond gets priority. So in this case, we would assign this molecule as this group getting priority number 1, this 2, and this 3. Okay, so here's a test question. If you had the following groups, how would you rank them? Which of these following groups has the highest ranking when precedence is assigned according to the rules we just went over? So if I was to look along these groups, I'm going to start with each of the carbons on the group. So in A, this carbon is attached to a hydrogen directly, and it has a double bond, so we call that being attached to 2 carbons. This next carbon is attached to a hydrogen, and it has a double bond to an oxygen, so it would look like this. This next carbon is attached to 2 hydrogens and a carbon. And our last carbon is attached to 2 hydrogens and a fluorine. So you can see some of the contenders. Remember, we're looking for highest atomic number. We already know that oxygen, for example, outbeats carbon. So these with just carbon and hydrogen are not going to float. But what about oxygen compared to fluorine? Fluorine actually has the higher atomic number. So even though there are more oxygen attachments here, that doesn't matter. Fluorine still has a higher atomic number, and so answer D would have the highest ranking when precedence is assigned. Okay, we're going to determine the absolute configuration of this molecule. I've already drawn out the priority of the molecule, but we'll go through it. So the best way to think about this is, remember, if the hydrogen is put in the back, we could draw this instead in this manner with our CH3 here, our OH here. This is our other group. And if we want to rank these, the oxygen will get priority 1 because of its atomic number. This chain gets priority 2. It's a longer chain. It has more carbon attachments than here, where we only have a carbon attached to 3 hydrogens. Priority 3. Now remember, once you assign the priorities and you have it in this configuration with our hydrogen pointing away from us in the back, we're going to draw an arrow connecting from 1 to 3. And this arrow is going counterclockwise. So it is an S configuration. Now, what about this molecule? Now, the first thing I've done on this molecule to help show you its configuration is I've flipped it around so that the hydrogen is pointing to the back. Notice all I did is I redrew it mentally, just taking everything and flipping it, not changing the order of anything, so that the hydrogen is pointing away. So this is the same molecule. I've just flipped it around. Now my hydrogen is pointing away, and I'm going to assign positions. So again, my OH gets the 1 position. It has the biggest atomic number. And then when comparing these carbon chains along the ring, you can see that when going along the ring, this has a double bond. And so this side will get higher priority than this side. And so after assigning priority, draw our arrow. And again, this is going counterclockwise, and so it has a configuration of S. Now, if I wanted to think about what this molecule would look like if it was in the R configuration, it would be, remember, the mirror image of this molecule. And so it would be drawn similar to how I drew my flip, except you'd see that we're going to keep the H in the front. So by just having the hydrogen still wedged in the front and our OH in the back like that, notice that these are mirror images, and so these two are enantiomers of each other, whereas this, I just flipped the same molecule. I made sure to also flip the OH and the H when I flipped it around. If you do not flip the OH and the H, but you flip the rest of the molecule, you've actually generated the R configuration, or the enantiomer of that molecule.